Welcome back. Now let's talk about derivatives in motion. And we're still dealing with vector valued functions. So let's say we're given some position vector, r of t, with these parametric components, so f of t I plus g of t j plus h of t k. So this is a position vector of a particle moving along a curve in space. Each of these three components, f, g, and h, are all differentiable functions of t. So let's look at the difference between time and then some future time. So what we can say here is then the difference between a position at, say, t, and then further along t plus delta t. So that would be the vector. We would say, well, that would be r of t equals that future position, which is r of t plus delta t, minus the original position, r of t. So considering these as components, this logic is going to help us derive the definition for derivatives of vector valued functions. And there is derivation of this in your book, but it's kind of long and drawn out. But so I'm going to kind of skip over it. But you'll notice this maybe x plus h minus some function of x looks kind of similar to what we put in our limit definition of a derivative. So let me pull our definition in. So given the vector function, as long as it has a derivative or is differentiable at that point t, and f, g, and h also all differentiable, then the derivative r prime of t, or using a different notation, the derivative of r with respect to t, is going to equal the limit as that change in time approaches 0. And then we have r of t plus delta t minus r of t over that change in time, our horizontal change. So as I said a second ago, and actually I should circle this differently, I should circle all of this. This should look really similar. It looks like our limit definition of a derivative. Remember, we talked about that in Calc 1, the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. All right, so we're going to define derivatives in the same manner. It's just that now we have these vectors. Remember, the bold letters mean vectors. So really, all the shortcut part of this definition is saying is, hey, differentiate each of those parametric components. So we have the derivative of f with respect to t, the derivative of g with respect to t, and the derivative of h with respect to t. These two notations here, r prime of t, dr dt, they mean the same thing. I could also write just r prime without the t, or I could write the derivative with respect to t of the vector r of t. There are lots of different ways that we can note or notate derivatives. These are all just different ways. And so you just want to always make sure you know what you're looking at. So let's continue along here and consider this limit definition of a vector derivative geometrically. So again, we've got our graph. We're going to think about it in 2 space, even though we know these vectors can move in 3 space. So we have some curve, C. And this first vector is going to a point P on the curve. I will call that vector R of T. And maybe I have a second point coming over here to some point we'll call Q, and that vector would be R of T plus delta T. So that is a vector of t at a future time. So if we looked here at connecting from P to Q, that line, we could call that the secant line. And that is, close to the definition of a derivative. Remember that secant is close to or close in slope, similar in slope to the slope of the tangent line. So what would our derivative vector look like? So I started drawing that not the way I want it. So r prime of t, this tangent vector, that is tangent to the curve at that moment, right, at P. So r prime of t is a vector tangent to the parameter curve at the tip of r of t. So right here, where r of t touches our curve C at point P, we have that tangent vector coming off, right? It's always going to be pointing in the direction of that increasing parameter. So, we can redefine this, state this definition a little more simply. If R of t is created by these components, f of t, g of t, h of t, or rather f of t I plus g of t j plus h of t k. Then what we can state for r prime of t is it is f prime of t I plus g prime of t j plus h prime of t k. So all I was doing there was just restating our definition for finding the derivative of vector value functions. So I mentioned earlier in this video, I said we're going to call this r of t a position vector. And you may remember from Calc 1, the derivative of position is, pregnant pause for you guys to all answer, velocity. So in the next slide, we're going to talk about this position vector and what the velocity and maybe acceleration vectors might look like, and we'll do an example with that. So if we let r represent a position vector of a particle moving along a smooth curve in space, then the derivative of r with respect to t will represent v of t. So this is the particle's velocity vector. The velocity vector, tangent to the curve, remember the derivative is going to be the slope of the tangent line when we're thinking back into Calc 1. So the velocity vector is tangent to the curve at that point. At any time t, the direction of v represents the direction of motion. The magnitude is going to be the particle's speed. Remember, magnitude, or speed I should say, is always positive, magnitude being a distance. So that length of the vector is going to represent the speed. And the derivative of velocity, the derivative of v with respect to t, will give us a being our acceleration vector. So velocity is the derivative of position. Speed is the magnitude of velocity. Acceleration is the derivative of velocity, or the second derivative of position. And then our unit vector, the velocity vector divided by its magnitude, is the direction of the motion at time t. So let's do one pretty simple example where we're going to pull in vector derivatives and then apply them in a velocity, speed, and acceleration context. So in the last example that we do in this video, we're going to determine velocity, speed, and acceleration of a particle whose motion in space is given by this position vector r of t. And then once we're done, I'm going to pull in a picture to help you visualize what the velocity vector in the original position vector looked like. And we're going to say, well, what is that velocity vector at a specific moment, in this case, 7 pi over 4. So the first thing we'll do is find velocity. Velocity is just going to be taking the derivative of each of these terms. So the derivative of 2 cosine t, that is negative 2 sine t, I. Derivative of 2 sine t is positive 2 cosine t, j. And then the derivative of 5 cosine squared t, we need to use the chain rule to find that. So the 5 can go out in front, and I would just be looking at the derivative of cosine squared t, or rather cosine t, quantity squared. So using the chain rule, that would be 2 cosine t to the first, and then the derivative of cosine is negative sine t. So this is negative 2 cosine t sine t. Multiplying that by the 5 we have up there, this will become minus 10 cosine t sine t k. And that last term we can simplify just a little bit right here, because this is 5 times 2 sine t cosine t. And we know by some of our trig identities, this is sine double angle. So this is the same as 5 sine of 2t. And I'm really just doing that simplification now so that this will be easier for me to take the derivative of than up here. Here I'd have to use the chain rule and take the derivative twice. So applying a little bit of a trig identity, when I go to find my acceleration vector and I take the derivative of the derivative, it'll be a little bit easier. So I'm going to erase that, and I'm left with minus 5 sine of 2t k. So that is my velocity vector. Let me find my acceleration vector. So my acceleration vector, I'm going to take the derivative of each of these parametric components first. So the derivative of sine is cosine. I've got negative 2 cosine ti. Derivative of cosine is negative sine, so I have minus 2 sine t j. And then the derivative of sine of 2t, we've got minus 5. The derivative for sine of 2t, that's going to be cosine of 2t times 2 using the chain rule. So I've got negative 10 cosine of 2t k. So I have my position, velocity being the first derivative of position, and acceleration being the second derivative of position. Position, velocity, and acceleration vectors. We're also asked to find the speed, and the speed is going to be the magnitude of my velocity vector. And the magnitude, that's going to be 4 sine squared t plus 4 cosine squared t plus 25 sine squared 2t. Here, I'll just use a little bit of algebra to simplify this. If I factor both of these 4's out, I'm going to have 4 times sine squared plus cosine squared, which by the Pythagorean identity is equal to 1. So I have the square root of 4 plus 25 sine squared 2t. And that represents my speed, the magnitude of velocity. And so at time t, so at time t equals 7 pi over 4, which we stated in the beginning. So we're asked to, sketch the velocity vector and find these vectors at 7 pi over 4. So velocity at 7 pi over 4, v of 7 pi over 4. Simplifying that, plugging it in, and simplifying these trig functions, 7 pi over 4, sine of 7 pi over 4, cosine of 7 pi over 4, sine of 7 pi over 2, 7 pi over 4 being sine of 7 pi over 4. 7 pi over 4 is in quadrant 4. We're going to end up with negative root 2 over 2, which gives me positive root 2i. Cosine would be positive, so that gives me positive root 2j. And this would give me a negative 1, so I'm going to have plus 5k. My acceleration at 7 pi over 4, similar argument, I end up with negative root 2i plus positive root 2j, and cosine at 7 pi over 4 plugged in here, that would be down at 270 degrees. We get 0, so that term goes away, and we do not have a 0. And then my speed at 7 pi over 4, if I plug 7 pi over 4 in here and evaluate this, I get root 29. All right, so what does this look like in perspective, or considering that original position vector? So here I have pulled in a picture. This blue vector represents the position of this particle moving in space. And at this specific moment, at t equals 7 pi over 4, we see that tangent vector, the derivative at 7 pi over 4, being tangent to that position point at 7 pi over 4. And so one other thing just to note, let me move this picture over so I have a little more space. So one little note, velocity is speed because it is a vector. So it has speed and direction, magnitude and direction. And that could be represented as the magnitude times the direction, which would be that velocity vector divided by itself. We said the unit vector is going to represent direction. So that should make sense to you because it's a balanced equation. So velocity of a moving particle can always be expressed as the product of its speed and direction. And to round out this video, we're just going to talk about some differentiation rules for vector functions. So just like we have constant rule, scalar multiple rule, sum and difference rule for regular differentiation, we also have differentiation on vector functions rules. The derivative of a constant vector is the zero vector. Scalar multiple, you can still pull that out in front and just take the derivative of a vector. Also, if that scalar multiple is a function, so we have a function of t times a vector of t, then we're using that product rule. So the derivative of the function times the vector plus the function times the derivative of the vector. The derivative of the sum of two vectors is the sum of the derivatives. Same for the difference, just that order matters when you're subtracting. So then we have the derivative of a dot product, first, second. First times the derivative of the second plus second times the derivative of the first. And the order doesn't matter so much with dot product. You're going to get u dot v, v dot u is going to give you the same value. However, with a cross product, U cross V, order does matter. So I've got the derivative of the first cross the second vector plus the first vector cross the derivative of the second. And then the chain rule, derivative of the outside, U prime of f of t, times the derivative of the inside, f prime of t. The proof for rules 5, 6, and 7, that's all in your textbook. The first ones are pretty simple to prove. I'm not going to do those in the video. We wouldn't have time to do them in the class. But if you're interested, please check them out in your textbook if you want to really have a good understanding of how and why they work. All right, so one more video in this series, we're going to talk about vector functions of constant length.